Good morning. Welcome to Physics 4B lab. What we're going to be doing each week in the lab is we're going to be coming in and doing some sort of a measurement. So today's lab is called thermal expansion. That's the title. And the objective we have for the day is to measure thermal expansion coefficients. So we've been talking about that in class, in lecture, and each week in lab what we'll be doing is coming in and we'll be looking at some topic that we've been talking about in lecture, and we'll be doing some measurements. Now I know that sometimes in laboratories kind of the idea is we're checking or double checking some results of somebody else. We don't want to think about it that way. The way we want to think about this is, hey, we've been assigned to come in and do some kind of measurement. Let's do it. And let's everything that we do in lab for the day is going to be geared towards meeting our objective. It's going to be geared towards getting the best measurements we can for the particular samples that we've been given for a particular measurement. So for example, today's lab, thermal expansion, it says that we're going to be looking at different metal samples. Now the samples we've been given look like this. We've got 3 of these metal samples, and our best guess as to what these consist of is we're guessing we have an aluminum sample. We also have what is we believe to be nickel, and then a third sample we have is copper. So we've got 3, I know it could be valuable, right? We've got 3 different metal samples that we're working from. Now, kind of the approach we're going to take in lab is, hey, let's say we're working somewhere and we are asked to, we've just manufactured wherever we're working. We've been part of a manufacturing team. We've come up with these new metal samples of some sort. We don't know for sure if they're pure. We don't know if there's some type of an alloy. Again, we're guessing they're aluminum, nickel, and copper more or less. We're going to go in and do measurements. So imagine you've been assigned to come in and do kind of the first measurements of these. So, one thing I always want to point out in lab is that we're not trying to get some particular number with our measurements. I'm always a little concerned that you guys in your lab classes are always just rewarded for getting the right measurement or the right answer in lab, and that's actually not the way science and engineering works. If we're going to actually try and discover new things, we have to independently do a set of measurements. So anyway, that's a kind of a theme we'll probably be coming back to. Now, let's take a look at what we've gotten ourselves in to for the day. So what we're going to say is, hey, we've been talking about this in class, and again, it's always going to be some topic we've been looking at. And what we've said is that as the temperature varies, we're going to start with some sample and say that its length is L0. So that seems pretty straightforward. I get out a meter stick, and I'm going to be able to measure the length of this. So I'll figure out what the L0 is. But then at the higher temperature, what's going to happen is we're going to have a little bit of thermal expansion. Now, it's not going to be a lot. At the most, it might be a millimeter or a millimeter and a half, something like that. It may not even be a millimeter. It could be a small amount. The temperatures that we're working between here are going to be somewhere around room temperature and 100 Celsius. So what we're going to be able to do is this. We're going to be able to make use of these devices. What they're called are steam jackets, and they're specifically designed for doing the types of measurements that we're doing today. So the idea is this. We can take one of our samples, one of our metal samples here, and what we can do is place that inside here. So I'm going to take this steam jacket off. I'm going to put the metal sample into one of these rubber stoppers, and then I'm going to slide the sample through. I got another rubber stopper on the other side. So So here's kind of what the setup looks like. Okay, so I've got my metal sample inside, I think it was the aluminum one, that I've placed inside here. I got rubber stoppers on both sides. I'm going to place it back in this support structure. Okay, so that's what the setup looks like. Now, what we've got at each end of this setup, of this support structure, is I have these threaded screws that are able to come in and just make contact with one of the ends of these. So I could rotate these in and just make contact, or I could rotate it back out so that it's not making contact. What I'm going to do is just rotate these in until they just make contact. Now I haven't got the full setup here yet. We'll see that later. We'll go in and do some close-ups of this setup. But what we're going to do is we're going to connect a voltage source, a battery, and a light bulb. And when these two are making contact, the light lights up. And when they're not making contact, the light goes off. So we can tell when we're making contact on the two ends and when we're not. So the idea is this. We're going to start off with these metal samples somewhere near room temperature. Now I got some thermometers on the table over here. I didn't grab one with me right now, but we're going to put a thermometer inside here. And then what we're going to do is there's a connection right here where we can push steam. We're going to have a boiler. We're going to have some steam forcefully being pushed through this steam jacket. The thermometer is going to keep track of the temperature variations that take place. And what we find with our steam jacket is it's going to start off somewhere around room temperature, 22, 23 Celsius. And by the time we've sent a lot of steam through here, the temperature inside is going to rise up to around 100 Celsius. So that's kind of the temperature increase that we're going to see. Now, in order to see a thermal expansion effect, the thermal expansion effect that we'll see is going to be proportional to the temperature. These are the equations we've been working with in in lecture and in the homework. Now, currently the way this is going to work is you guys are welcome to be working together in lab groups, but I'm probably going to be everybody's lab partner because I have access to the lab. And I'm going to be able to go in and actually carry out the measurements, the direct measurements. And so I'm going to be everybody's lab partner. Now, I'm a good lab partner to have because I'm always staying caught up in the course. I've read chapters, I'm already through chapter 17. I've taken a look at the homework problems, and I understand, basically, what thermal expansion is all about. These are the formulas that I've watched in lecture and that I've played around with in some of the homework. And so in order to come up with a thermal expansion coefficient for these samples, it looks to me like there's three things that we need to make sure that we're keeping track of in our laboratory measurements. It looks like we need to be able to measure L naught. And L naught's not such a big deal, right? I just get one of these metal samples. Again, I can grab a meter stick from over here, and I can measure what L naught's going to be. The other thing I have to measure is I have to measure delta T. So I put down L naught. I put them kind of in order of increasing difficulty. I'm thinking L naught, no problem. I can get L naught measured very accurately. What we would like to do in this lab, and it's kind of a rule of thumb for all the labs that we do in the course, we would like to be able to keep our accuracy within about 1%. Now, that's a bit of a lofty goal. So we probably seldom actually consistently are able to do 1% measurements, but kind of the thinking here is if every measurement we make, we're trying for that 1% accuracy, 1% precision, we'll do better than if we're not paying attention. So again, kind of the mindset here is we want to be able to get measurements that are accurate to within a few percent. And that requires us to try and get 3 significant figures on every measurement that we take. That means 3 digits of precision. So let's think about that. can I measure L naught in a way where I can get 3 digits of precision? And I've measured these. I'll get the meter stick out and measure them again. But when I'm measuring with the meter stick, this is going to become something like, I think, most of these samples. Now, they're not all identical. There's a little variation, but the samples I've been looking at are very, very close to 600 millimeters in length. Now, that's 3 significant figures because I'm measuring the 6, the 0, and the other 0. So they're very close to, in fact, I think they were manufactured this way. So I'm going to say that the L naught was 600 millimeters because that's what I measured with the meter stick. And yes, that gives me 3 digits of precision, and that's going to maintain kind of this 1% accuracy or precision in our measurements. Now, what about delta T? Well, delta T is keeping track of what was the temperature that we started at, and then what was the final temperature. Now, delta T could be something like, let's say this. I'm going to try and squeeze this in here. Let's say that the starting temperature was 22.1 Celsius, and that the final temperature, let's say the final temperature reads out at 100 I'll say 100.2 Celsius. Now our thermometers, let me change that actually. What tends to happen here is that we don't actually go over 100. It's more likely that we have readings that are a little short of 100 on this lab. So I'm going to do this. I'm going to write in 97.6. All right. Now, if the kind of the starting temperature is 22.1 and then the final temperature is 97.6, what will happen then is I'm going to take the difference between those two, and it looks like it's 75.5. If you guys ever catch me making errors on these videos, let me know right away, and I can go back and at least send out an announcement. It's going to be difficult to go back and edit some of these things, but I'll do what I can. So that's going to give me a delta T. So again, we're trying to get 3 significant figures, and in order to do that, I got to measure using these thermometers down to 0.1. Now this number seems pretty good, except for the fact that our thermometers aren't that accurate. It turns out that if I just take a bunch of our thermometers out of our thermometer drawer over here and kind of place them side by side, I'll see variations of a half a Celsius, maybe even more, maybe almost a Celsius difference between them. And so we're going to write down these 3 significant figures, knowing that there's still going to be limitations beyond that. We're going to take that into account when we talk about writing up our lab reports and our error analysis and the limitations that we're running into. But for right now, we're going to maintain that spirit of getting 3 significant figures on every measurement till I've got it. Now, this seems very easy and reliable. I'm not going to be off by a millimeter on this, so I'm going to be fine here. This, I just realized, is going to be a little more difficult, but even if this is off by a half a Celsius, when I think in terms of percent uncertainty, it's still going to be around 1%. This is the tough one right here, is delta L. So delta L, you might think what delta L consists of is measuring with a meter stick and then letting the temperature go up and then measuring again with a meter stick, but that turns out not to be very reliable because the meter sticks can't really measure that accurately. So we're going to need something better than a meter stick. And what we have are these steam jackets. So remember we talked about with the steam jackets attaching a light bulb and a battery, and then we could very carefully rotate these contacts into the piece of metal, the metal sample. And what happens is at one end, we have one of those contacts where we just rotate it in and leave it there. That's important. And then at the other end, what we can do is, at the beginning of the experiment, when we put the sample in and we do the initial temperature measurement, what we do is we rotate this in until it just barely touches. When it just barely touches, I read, there's two different scales here. There's a circular scale and there's a plate. Now, I've drawn a big picture of that because this is such an important part of this laboratory experiment. The circular scale looks like this. It goes from 0 all the way to 100. Now, what that's measuring is hundredths of millimeters. The threading on this scale, on this circular rotatable scale, the threading on those is a 1 millimeter spacing between the threads. Every time I rotate that once, it moves forward or back by 1 millimeter. And since this scale is keeping track, it's breaking up that one full rotation into 100 pieces. Those become like hundredths of millimeters. And if I'm going to maintain 3 significant figures of reliability, of precision or accuracy, I'm going to need to be able to measure down to hundredths of a millimeter. So at first thought, I would think that's a pretty difficult measurement to make, and it is, but this actually makes it doable. Now there's still some limitations built into this, but it does a pretty, it's reasonably reliable. So we'll see how much variation we end up with. Of course, I'm your lab partner. I'll be doing a lot of these actual hands-on measurements. But you guys will be able to see, I'm going to go in and do those measurements, and you guys will be able to see how much variation there is from one run to the next. So I wrote out an example here. Let's say that I go in, and initially, using this scale, I measure 6.42 millimeters, and then what has to happen while I'm heating this up is that this scale needs to be rotated out. That scale's got to be rotated outwards because I have to allow room for the metal to expand inside here, right? If I have these two contact points pushing on the metal, then what's going to happen is that the metal it's going to bow a little bit maybe. It's not going to have enough room to separate out. Now there's a bar down here which is holding the two ends together. And we're assuming in the lab this is far enough away from the steam jacket that this remains at a constant temperature. We don't want this expanding. If this support structure expands, that's going to create problems for us. So we're expecting that this does not expand. Now the steam jacket itself is going to expand a little bit, and the metal inside will expand. And we need to make sure that the stoppers at the ends are not stoppered too tightly. If they're stoppered really tightly, we're going to run the risk again that the metal sample inside is not free to expand by however much it wants to expand. So I'm going to leave a little bit of a gap here so that it freely expands within there. Okay, that's the plan. That's what we're setting this up to be able to do. Okay, and again, we'll be doing a close-up of this. For most of these labs, what's going to happen is we'll have a video where we kind of do an introductory something from the board, kind of the theory behind it, what do the tables, data tables, results tables look like, what does some of the equipment look like, and then we'll follow up with some close-ups of actually running the experiment. Okay, so we'll be over there doing that in just a bit. But anyway, this is, and then as questions come up, I know that there's going to be a little bit of a delay here. You're not able to ask questions right away, but definitely stop by office hours, lab hours when I'm on Zoom. And that's most of the day on Monday, Wednesday, Friday right now. So stop by those office hours and ask questions. You know, stop by. If you guys end up forming lab groups, which I'm hoping you will, and I can help out with that if people have questions. You know, come by as a lab group. Everybody stop by, decide when you're going to stop by, and just come into the Zoom meeting. I will be there, and I get questions answered as they come up. All right. So what we did was we measured before and after. We measured at the low temperature. We measured at the high temperature. We did see a difference in what I'm calling X. Now X doesn't really mean much. It's really the difference between the two X's that's meaningful. So one of these X's by itself just means, you know, when I put this metal sample in, just by chance, what was the number that went along with that placement. But by the time I've measured two of these, one at the high temperature, one at the low temperature, what that difference is going to tell us is how much expansion did I have. So the expansion I'm seeing here is 1.43 millimeters, and that's actually that's a good amount of expansion. This, you know, if this is for aluminum, or I think aluminum does tend to have a larger expansion coefficient, we might see something this high. I don't think we're going to see anything any larger than this. So most of the expansions are a little above a millimeter or a little below a millimeter, kind of in that range, given that the starting length is 600 millimeters. Okay, so that's our plan. So the idea is to do everything we can to maintain those three digits of precision everywhere. What happens if this is measured very reliably, this is measured very reliably, but this is this has lots of error in it? Well, if any one of these measurements has a lot of error in it, it's going to undo our efforts on the other two measurements. So you've always got to think in terms of keeping, you got to kind of keep the measurements consistently good across the entire, you know, one set of bad measurements with one of these measuring devices can throw off everything else. Okay, so and that's an important, you know, that's an important idea within science and within engineering and doing measurements, identifying which measurement is going to be the most difficult to make and which one is going to have the least reliability to it, and then put a little extra effort into those measurements. All right, so for the data tables, it looks like I'm thinking that we need to measure L naught, we need to measure starting and final temperatures, we need to measure, and let me do this. What I like to do, at least on the board here, is identify, correctly I hope, what are the direct measurements. So in fact, I didn't write direct here. Okay, so what I've done is I've put little red marks along my data table. Those columns that specifically are the direct measurements. Those are being made by some measuring device. The length is from a meter stick. The two temperatures are from the thermometers. The X naught and the X are from this rotating scale. Ooh, I almost forgot. Along with this rotating circular piece, right next to it is this flat scale, and the flat scale is just reading millimeters. So we said that every time this thing rotates once, it either moves in, or depending on which direction we're rotating, inwards by 1 millimeter, outwards by 1 millimeter. And you can see that as I do that, it just moves back and forth along the scale. So in that example I have there, the first digit, the 7, and then on X naught, the 6, is coming from the flat scale. So that's coming from the flat scale, and then those last two numbers are coming from the circular scale. So these are coming from reading the circular scale. All right. So this is what the data tables are going to look like. Now, when we do a measurement, if we do it once, we're really not sure how reliable that was. I mean, we may have done everything very carefully and feel like everything went pretty well, but it's so useful to come back and do a second and typically a third measurement. By the time we've done 3 measurements, we're starting to get a pretty good idea of how much reproducibility there is in the set of measurements that we're doing. So that's going to be our plan for the day. For each one of the 3 samples that we're working with, we're going to do 3 runs. So we'll do a first, a second, and a third run. Now I'm actually going to get the meter stick out 3 times and measure the L naught 3 times, just to, make sure that I'm doing everything for each one of the runs. I'm going to measure that. Now the T naughts and the T's could be different on each one of the runs, right? In between the runs, we are going to have to take the steam jackets. These are going to be like at 100 Celsius by the end of the run. And that means that we're going to have to take these out. We're going to have to remove these, and then run it over to the sink, run a bunch of cold water into it. Be careful, do not get burned. We have hot pads around. You'll see those when we get over to the tables. We're going to have hot pads there, and make sure that there's a clear path to the sink, because you don't want to run into other students along the way. So make sure you got a clear path. Warn people, grab that 100 Celsius steam jacket, run over there, run some cold water over it. So far, we've never, I'm trying to think, I don't think anybody's ever been injured by this, but be careful with the setup. And so we'll run a bunch of cold water through it, we'll bring it back down to room temperature, and then we're ready to go. But the temperature, starting temperature by then, could be different. So these entries could be different, these could be different, if our thermometer, the steam coming through looks different. And then the X naughts and the X for sure are going to be different on each one of these runs. And then we'll measure, we'll calculate the delta T, calculate the delta L, and come up with alpha. Now, units are going to be really important in all this, and I think in the notes that I'm going to put on campus, you guys are already on campus tracking this video down. There's other stuff with this lab module. So you guys have probably already discovered that each one of the labs has a different module, and within that module there's a set of resource documents, and you're going to need all of them, I think. So, and I'll probably be paying closer attention to units as we do that. Now there's also going to be a results that we're going to get from this, so here's a results table. And the samples are aluminum, nickel, and copper. And so, and just to check some of the material properties here, I have a scale over here. I've been trying to do density measurements just to check and see if it's, reliably the metals that we think it is. Each one of the samples. And then also one of the kind of fun things you can do with these metal samples is some metals are what we call ferromagnetic. Like iron is very ferromagnetic, and nickel is ferromagnetic. There's a handful of materials that are ferromagnetic, and but others aren't. So here's aluminum, does not react to our Laney super magnet, and but look, the nickel responded. The nickel is ferromagnetic. So just checking out some of the material properties to see what these samples consist of. All right, results table. So here we're going to get down to what did we find out about the samples, because we've got a data table for each one of the samples, and I've done 3 runs on the aluminum. There's another data table with the copper, another data table with the nickel, copper, aluminum. And so here's the results that we're ending up with. By the time I get to this coefficient here, I want to take the average. So I want to take the average from those 3 measurements. Now I'm hoping each run gives me something kind of similar. Maybe it will, maybe it won't. We'll just see how the precisions work out. But so we're going to get an average value from that. That is going to become our measured values. So our overall measured values for the day, the ones we're going to report back to our supervisor, is going to be the average values from those 3 runs with each one of the different samples. Now, most weeks when we're in lab, when we're doing these measurements, I'm going to say much of the time, maybe most of the time, there's an accepted value. Other people have done similar measurements, and we are going to do a comparison. Again, this is not the idea of, I want to get as close to the accepted value as possible, but rather just thinking, I wonder if our sample is really what we think it is. Maybe we should compare with other people who've done these measurements for these materials and see if what we're measuring for our samples corresponds. I mean, maybe that's a way to check and see if our samples are kind of made out of the same material. So in any case, we're going to take our measured values and then compare them with accepted values for what we think the samples are. And then we're going to do a percent difference. So percent differences are really handy. What they do is they allow us to say very quickly, what we measured was 5% higher than the accepted value, or our measurements were 3.1% lower. So that's a very quick way that's independent of units. So it doesn't depend on units. It's a relative number. And we get that by taking the measured, subtracting off the accepted, and then dividing the whole thing by the accepted, multiplying by 100. Now, you may have seen these types of percent difference formulas in other classes, in other labs that you've done. And there are some small differences between them. The version I like, the version I prefer, is the one where we're saying, what is our measurement relative to the accepted value? And that's why in the denominator I've used the accepted value as the reference. So the way this works, also, it can be positive or negative values. So if we're getting values higher than the accepted value, that's going to come out as a positive value. If we get numbers that are lower than the accepted value, that's going to come out as negative. So we can get things that are higher or lower, and we can represent those as a positive percent difference or a negative percent difference. Go ahead and leave the plus and minus signs in there, please, so we can see if we're coming in higher or lower than the accepted values. Okay, and that's kind of everything for this week. Now, the way the labs will work is, again, I'm hoping that you guys are going to be meeting up with your friends and forming lab groups. And if you're not, you don't know anybody in the course, or you can contact other people in the course, or we can put some lists up, and you can work together with groups. It's always nice to work together with groups in lab, because then you can catch each other's mistakes, is the idea. So the idea is that everybody's running all the calculations, everybody's doing the graphs, and you can compare numbers and see how that works. So let's move on to lab reports. So now everybody is required to produce their own lab report. So there's not one group lab report that gets turned in. Everybody should write up your own lab reports. And the format that I prefer for the lab reports, and I'll probably have an example of this. There's an example of this on Canvas. It should be there. I should have some examples written in. Title and objectives, start off with those. And then I actually prefer having a results table right after that. And I don't think lab reports are like suspense novels, where you have to wait to the last chapter to find out what happens. I prefer this, I guess. I prefer saying, this is what we set out to do, and then immediately follow that up with, and this is what we got. Now you might think, well, wait, don't you want to say how you got there first? And I actually like to know what the results were first, because then when I look at the data tables, if I see something in the results table that catches my attention, that helps direct me as I go through the data tables and the limitations. So I want to start thinking in terms of, I want to take a special look at the graphs, or I want to look at these calculations once I've seen the results table. So anyway, results table. Now, typically along with the results table, it's good to put some comments. And the comments can be very simple. The comments could be something as simple as, all the measurements we did were actually within 3% of accepted values. It's consistent that these materials are made, they're the materials we think they are. Okay, something like that. If you've got two samples that come in very close to accepted, maybe one really stands out. Anyway, just a quick comment to let people know that you've looked to see if there's any pattern in the results that you've come up with. So, results, data tables, limitations. So the limitations are just an error analysis. Now, if your number doesn't match the accepted value, that's not an error. So if the numbers don't match up, then we want to try and find out what are the possible, what's our possible understanding as to what's the, how are these two numbers related. But we always want to think in terms of what were the limitations for the numbers that we came up with. And the limitations in what we came up with, the first thing I want to look at are the direct measurements. Now, we talked a little bit about direct measurements. Those are the ones that are being made with, well, today it's the thermometer, the meter sticks, anything where we're actually using a measuring device to come up with that value. Each measuring device has a limitation sort of built into it. Our thermometers, for example, have a limitation of about 1 degree, plus or minus a half a degree, or to be conservative, we'll say a full degree. So we should list those, and again, the examples that I have on Canvas, take a look and see what those numbers might be for today's lab. And then also assumptions. Now, if you think about today's lab, what are some of the assumptions? And sometimes these are things that are obvious, and other times they're not. One of the assumptions I would think we're making today is that when we have a metal sample inside here, the entire length of the sample is at the same temperature, and that temperature is whatever the thermometer is reading. Now, the lower temperature, when it's at room temperature, that's probably true. But when we go to the high temperature with steam being pushed through this device, I begin to wonder if it really is that the entire length of the metal sample, everything's at the same temperature. Not so sure if that's the case. Anyway, those are the kind of things, assumptions that we are making. I guess we're also making assumptions about, when the contact is a reliable representation of where the edge of the sample is located. So those are good things to start from. There's a couple things in the error analysis that you don't want to include. One of those is writing down human error. What I find when I'm looking at lab reports is that it seems to be kind of a strategy that students have, thinking, oh, I'll just write down human error. Nobody can argue with that. But writing down human error isn't really useful for us. It doesn't tell us how much error we're expecting. It doesn't specifically say where the human error is taking place. So for example, in today's lab, if we're looking at the L0 value, I don't want to say there's human error in making the L0 measurement. What I want to say instead is that we were using a meter stick, and a meter stick, the measuring device itself, when properly used, has a limitation of probably half a millimeter, something like that. So rather than say it's human error, specifically say when this measuring device is being used, what is kind of the limitation that we're going to run into using that particular measuring device. Now, the other item that I don't want to see included in the lab report is don't say we may have made errors in the calculations. So the idea with calculations is this. You guys have calculators. Everybody in your lab group, you've checked the results, you've double checked, you've triple checked, you've compared numbers. By the time you're submitting your lab reports, you really shouldn't have any calculational errors left. Any calculational errors really should be taken care of. Of course, there's always, in any publication, a scientific journal, whatever, there's always some possibility that there's been errors in calculations that has taken place, but that's not something that we necessarily point to. Okay. So I know those are easy things, the human error calculation, those are easy things to write in, but don't write those in as examples. Okay, so again, any questions with the lab reports, with the formats? They're going to be due, well, they'll have due dates listed in Canvas, but typically think in terms of within 1 week. So within 1 week of the due date, within 1 week of the date listed for a particular lab, you should be turning in your lab reports. Okay. All right. And those due dates will you'll get announcements on Canvas. Canvas will remind you that you've got a lab report that's due and that's coming up. All right, let's move on now. So we talked about the lab reports. I'm going to get back to the direct close-up look at this lab. So let's do that. Let's look at actually carrying out the experiment. All right, so here we are with the close-up part of the experiment. So I've got here's our lab. And here's one of our lab tables. And what we're looking at is I've got a hot plate here. And I've got a container here that's got water inside. We're going to get that up until it's boiling and creating just a lot of steam. That's going to take a while, so we've got some other measurements we'll be doing in the meantime. Notice that I've got this beaker set up. That's going to catch the steam. Steam coming out of there is going to go into the beaker. Some of it will condense, just trying to make sure that the steam doesn't puddle up on the table. And so here is the steam jacket. I've got the sample inside here. I am ready to take measurements of the temperature. And here is that circular scale right there. So here's our best look at the circular scale, measuring hundredths of millimeters. And here is that flat scale. And the way I'm going to read those numbers is right at the junction of the two. So I'm going to look at where the circular number meets up with the flat number, and I'm going to get my millimeters and hundredths of millimeters from there. So that's the plan. And then here's the battery. Now I'm going to show you what it looks like when the light, there's the light going on, there's the light going off, and what I'm doing is I'm adjusting this contact. So that's what it's going to look like when the light goes on. All right, and there's the battery and all the support. Okay, so that's a look at the setup. I'm going to go ahead and take a couple numbers here. So these are the numbers I ended up with. I read the thermometer, and the temperature, starting temperature, it is chilly in here today, 17.1 Celsius. So campus is pretty much shut down, and there's no heat, and I didn't realize it was really that cold. And then for the X naught that goes along with that, I read off 11.06. Now what I've done is I've opened that gap up so that I'm going to allow for a couple of inches, well, I'm going to allow for a millimeter or so of expansion. I opened it up several millimeters to make sure there's room. And then at the other end, I am not touching that. So I don't want to touch that reference. That end needs to stay in place, and I've left enough slack or looseness. And now it's just, it's a game of waiting for this boiler. The boiler's leaking a little bit of water. I can hear that coming up on the hot plate. But so far, no steam. Now, I ran this before, and it was perfectly capable of generating the steam, so I think we're going to be fine with that. But once the steam starts shooting out of here, I am going to grab hold of that hose, and I'm going to plug it into the steam jacket, and we'll see what it looks like. Steam shooting through this device now. This is all looking pretty good. I've got steam that's coming through. You can see the steam exiting through this hose over here on the left. I'm just about to go in and do the measurement here. I'm going to reach in here and show you what that's going to look like. I'm going to be rotating that circular scale, reading that off, and I'm going to make it so that it just touches At the same time, I'm going to be reading the thermometer. It looks like it's almost leveled off, and I'm reading somewhere around 98.5 maybe as a temperature. I got a little bit of a leak on this side that I was concerned with at first, but it looks like that's not an issue. The temperature inside has gone up, and I can see steam coming out the other side. So I'm just going to take these readings right here. Let me take a look and see. I am going to just bring that light so it just turns on. And the reading I am getting now is, it looks like it is 12.20. So I'm looking at 1.2 millimeters of expansion, something like that. And the temperature that I am seeing, well, I'm getting like 97. It looks like it's actually around 97.4 is likely the reading I'm going to have. I'm going to give it a few more minutes here. These might not be the final numbers, but you guys, that's it. That's how this lab works. I'm showing extreme caution, you guys too. All parts of this now, the steam jacket at really high temperature. It's worth pointing out that a few years ago we decided to order a few more of these because some of the setups had become damaged, and it turns out they do not make these anymore because they were considered to be too dangerous. So, this is like the really dangerous labs that we're doing. Anyway, this is it. Any questions, let me know.